So here we have our introduction to biotransformation and biodegradation. So some terminology first. Biotransformation is the transformation of chemicals or organic waste into other chemicals or products. So this could be the storage of a chemical within an organism or the transformation of a chemical within an organism. But usually when people are talking about biotransformation, they're talking about biodegradation. So this is the biotransformation of an organic pollutant into other compounds, usually through respiration. Mineralization is another term you might hear. So this is transformation of organic carbon, nitrogen, or phosphorus into an inorganic form. So this, for example, would be turning organic carbon into carbon dioxide. So biodegradation, usually respiration. So as you now know, that is breaking carbon bonds to get energy. So oxidizing carbon and using a terminal electron acceptor, reducing the terminal electron acceptor, and getting energy from that process. And as you go sort of down this ladder, getting to more reduced conditions, organisms get less and less energy from reducing these terminal electron acceptors. Okay, and then this is just the product that's formed when the terminal electron acceptor is reduced. Okay, so here we have redox conditions under a leaking underground storage tank. So you have, this is a big organic plume, and on the outside you have oxygen available because that's what organisms want to use because it provides the most energy. But after the oxygen runs out, then they start using nitrate, kind of stepping down that ladder, then using iron, then using sulfate, and all the way in the middle of the plume, all that's left is carbon dioxide. So here is sort of a gradient of more reducing conditions and decreasing energy yield. Okay, so where will biodegradation be the fastest? You can think about this, hopefully not too unfamiliar of a question to you. And the answer for this is A, because that's where there's oxygen available and biodegradation goes the fastest there and the most energy is gained by using oxygen as a terminal electron acceptor. Okay, so biodegradation is usually done by microbes, and when people say microbes, they mean fungi and bacteria. They're a little bit different. Fungi are really good at biodegrading complex carbon, things like wood, but they need to have oxygen. They can't use the other terminal electron acceptors. Bacteria, on the other hand, are better at biodegrading simple carbon, but they don't require oxygen. They can use a range of terminal electron acceptors. So in this case, back to this plume, where is it that fungi can respire? At A, B, or both of those locations? And hopefully you remember, fungi require oxygen, so they can only biodegrade at A. Bacteria, where can bacteria respire? So you can think about that for a moment. And the answer is at A or B, because they can actually use any of these terminal electron acceptors to oxidize carbon. Okay, so to have fast biodegradation, one way to do that is to have low molecular weight, simple organic compounds, things like sugar. A maple leaf is a good example of something that occurs in nature that degrades fast because it has a lot of simple carbon compounds in it. Whereas wood is something that has very complex carbon, high molecular weight carbon. Which leads us into thinking about what slows biodegradation. So there are 4 factors that we're going to focus on here that can slow biodegradation. The first is biochemical recalcitrance. So that's the idea of complex carbon being more difficult to degrade. So something like sugar or amino acids are small and very easy to be used for energy. Something like cellulose, a chain of sugars, is pretty easy to use or to biodegrade. But something like lignin or bituminous coal is a very complex, high molecular weight compound. It's pretty hard to biodegrade, so it takes a long time. Another thing that can slow down biodegradation is when organic matter here is kind of stuck to soils via a cation bridge, which is what this is. So we've got negatively charged clay with cations stuck to it, and then organic matter, which is typically or predominantly negatively charged, sticking to those cations, and the microbes over here can't really pull it off. Another is protection within aggregates, within soil aggregates. So if you think about this, when you dig a hole, it doesn't come out as all singular grains of sand or clay. They form these big clods, so there's organic matter in those clods that is harder not just for you to get at, but also for the microbes to get at. And then finally, the idea of xenobiotic compounds, so otherness. So what does this mean? This means that xenobiotic compounds are essentially chemically synthesized, things we've made that have never occurred before in nature. Pesticides, herbicides, plastics, PCBs, fully chlorinated compounds. So microbes do have a couple things going for them in terms of trying to decompose these xenobiotic compounds. And the first is that this isn't exactly how biodegradation happens. The microbes don't sort of walk over to complex carbon and chomp it up in little bites. What they do is they send out enzymes outside of their bodies into the environment that go and decompose or break off little pieces of complex carbon, and it's these simple pieces that the microbes can take into themselves and use as energy. So the thing that microbes have going for them is that there are a lot of these enzymes out in the environment that they produce, and they can actually be pretty nonspecific. So it may be that eventually one of these enzymes will work on these xenobiotic compounds and break it up into smaller pieces that microbes can use for energy. The other thing is that bacteria adapt really quickly. They have extremely high growth rates, and they can also share genetic material between themselves. So if something works for a xenobiotic compound, they can actually pass that around and have it happen even more quickly. So what else do microbes need for biodegradation? These are things that you probably already know, so you can think about that for a moment. Things like enough water and the right temperature, and limiting nutrients, enough nitrogen and phosphorus. So just to kind of sum up, biotransformation is storage within or transformation within an organism, so that biodegradation is a type of biotransformation. And most biodegradation happens by microbes for energy, so respiration. So to have fast biodegradation, you can have low molecular weight, simple organic compounds, aerobic respiration, meaning using oxygen as a terminal electron acceptor, and knowing that having their needs met, enough nitrogen, phosphorus, the right amount of water, and the right temperature. So slow biodegradation can happen when there's complex carbon, high molecular weight compounds, carbon protection by soil, either by sorbing to soil particles or being physically protected in aggregates. If there's a xenobiotic compound, something that microbes can't decompose very easily, anaerobic respiration, or limiting conditions, not enough nitrogen, not enough phosphorus, too much or too little water, and too hot or too cold. And that is our introduction to biotransformation and biodegradation. Thanks for watching.